Let us start today's discussion regarding how to write the spectral notation and how the D1, D2 lines are written in terms of the spectral notation. So this is our lecture number 6. Let us start. The total angular momentum of an electron revolving around the nucleus of an atom results from the combination of its orbital and the spin angular momentum. If we consider PL vector and PS vector as the two angular momenta as we have discussed earlier, then capital L vector will represent PL vector and capital S vector will represent PS vector. And the combination of the two will give rise the total angular momentum of the electron. And this approach, that is, instead of writing PL vector and PS vector, we are going to write these things by capital L and capital S, which leads to the connectivity with quantum number, the orbital quantum number and spin quantum number. So this will lead to the vector model of the atom. Now, in presence of the magnetic field, this change, there must be a change of the PL and PS because the motion of the electron will be affected. And how those vectors will be changed by its direction, it leads to another very important discussion, which is followed by space quantization rule. The total angular momentum of one electron atom. What is the meaning of the one electron atom? Hydrogen is the simplest part of that. If we consider, say for example, sodium, we know the number of electrons is 11. Out of that, 10 number of electrons, it is under the core, and 11th is the valence, and it takes the part in several reactions as well as in transition. So for the single electron atom or one electron atom, because we will not consider the core part, it is totally inactive because very strong, very stable. The capital J, which is actually coming from the angular momentum Pj, so that J will be the sum of L and S vector. For a single electron, the spin quantum number is given as half, and that value. This value can be shown as half if we discuss the famous experiment Stern and Gerlach. Later on, we will discuss about that. In case of one electron atom, there are two orientations only possible because spin up and spin down. Single electron, there is no other possibility of the combinations of presence of the other electrons. So with respect to L vector, either S vector will be the same direction or S vector will be in the opposite direction of the L. And the magnitude of J can be either L plus S and L minus S. From the previous discussion, we have seen the several notations of L with respect to sub-energy levels, that is the sharp principal, diffuse fundamental, and that 0, 1, 2, 3, that is SPDF. And additionally, if we look through the L equal to 4, G, then in the other terms, higher order terms. So from those discussions, those SPDF, they are called the term values. What is the difference between the small s and capital S, or small p and capital P, or small d and capital D? Later on we will see that is from a single electron or the many electron system. We will just designate the terms accordingly. So for the single electron, if it is pth electron, then for the pth electron, L equal to 1 we know. And what is the magnitude of the J? It will either 1 plus half or 1 minus half, that is 3 by 2 or half. So for the p electron having L value equal to 1, the possibility of the transition, because we are going to discriminate about the several electrons, same p value, same L value, but how they can be designated by the several specific identity. Here is the one answer. So that p electron can have two distinct identity having its energy value as having J 3 by 2 and J half. These two different possibilities of transition are known as the multiplicity, and it is calculated as 2s plus 1 value or the 2s plus 1 factor. Here you check single electron, so s equal to half, so 2s plus 1 equal to 2. So here the multiplicity, that is in two ways the transition can take place. So multiplicity 2 arises the doublet, and the multiplicity 3, if it is there, we will investigate later on, then it will arise triplet. So what is the spectroscopic notation? So if we write down the term value SPD, the S corresponds L0, P1, D2. So J for S level, that is equal to half. J for P level will be 3 by 2 and half. J for D will be 5 by 2 and 3 by 2, because L plus S, L minus S. So accordingly, check here we shall write the multiplicity term, that the number of transition will occur in the two ways. The right, left, the two positions are there. Here the left up corner, here right bottom, that corner side. The two positions, this position will designate as its multiplicity, and this position will designate its J value. So this spectroscopic notation will be represented by S level with multiplicity 2, here J value half. Similarly, these two J values are written here as 3 by 2 and half with P state with multiplicity 2, because the two ways the transition can have its position. Similarly, for D state, the J values are 5 by 2, 3 by 2 with multiplicity 2 with term value D. So, in general, we shall write down, and it is one example, that is 2p 3 by 2 means here this symbol 2 just follow the position of the cursor. It is actually left horizontal. Left horizontal, that position, it designates the principal quantum number. As it is the P state, definitely L will be 1. As multiplicity is 2, then 2s plus 1 equal to 2, so S equal to half and J equal to 3 by 2. So it is the full designation of that electron in that state. Now, what is the meaning of D1 and D2? There are two distinct wavelengths. One is D1 5896, another is D2 5890 in angstrom order. In case of sodium, when the spectrum is seen in the visible range, and how they are formed, how the spectroscopic notations are there. Let us discuss. Well, how to remember which one is D1 and which one is D2? Very easy to remember. As I am first, so I am D1. So D1 is the highest value, D2 is the lower one. For that reason, D1 is 5896. In terms of the nanometer, it will be 589.6 nanometer. As the atomic number of sodium is 11, so 1 is 2, the principal quantum number n equal to 1, number of electrons 2. For 2s2 to p6, n equal to 2, so number of electrons is 8. And 3s1, n equal to 3, number of electrons 1. So here is this diagram for the electronic configuration of sodium in its ground state. So those 10 electrons, as I have discussed earlier, they form the core. And the 11th electron, it is the valence electron. This electron can move to other higher energy state which will be available for the required transition. So next immediate available state is 3p. Just look this diagram. After 3s, the next possible energy state is 3p. And what is the spectroscopic notation of that? 3 to s half, as I have discussed earlier just now. So L equal to 0, S equal to half, and J equal to half. For 3p level, L equal to 1, S equal to half. So those two levels will be designated as 3-2p half and a 3-2p 3 by 2, where those possible to energy levels are represented by these spectroscopic notations. So the electron can move from 3 to S half either to this level or to that level, the immediate two available energy levels. From 3 to S half energy state, the two possible transitions. First transition may be 3 to S half to 3 to P half. Just check the change in the J value, half and another half. So change in J value is 0. Here another possible transition takes place. Check the change in J value, 3 by 2 minus half, that is 1. And as the change in the J value is shorter, so less energy difference, so higher wavelength D1. Here the gap of the J values is more, so lesser wavelength or the shorter wavelength D2. So here is the selection rule. We have just noticed that a delta J change in the change in the delta J occurs in either 0 or 1. So it is the selection rule and it is totally the outcome of the experimental result, either 0 or plus minus 1. Similarly, the change in L value will be either 0 or plus minus 1. So this transition, it is D1, and this transition is D2, where delta L is plus 1 and delta J 0 for D1, and delta L plus 1 with delta J plus 1 for D2. Now when we will check these D1 and D2 lines in our laboratory, and there is a one experiment in SEM 5 in Calcutta University syllabus. Sodium D1 and D2 lines can be seen very clearly in our experimental lab using spectrometer and one grating having ruling of 300 lines per millimeter. Then two distinct yellow lines are seen in second order and third order of the grating spectra. If we increase the rulings of the grating, say around 600 lines per millimeter, then the gapping in between the two lines will be larger than the previous using the 300 lines per millimeter, this type of rulings, and the angular separation between the two lines can be measured using the corresponding experimental setup as well as theory. So next we shall discuss about the formation of other quantum numbers, that is when the electron motion will be affected in presence of magnetic field. Then how the quantum numbers L and S will be modified or will be extended. So up to this, goodbye.